I will now give some basic examples of Banach spaces and Hilbert spaces. So let E be a space, curly E, a sigma algebra, mu a measure. So this triple is a measure space. And we denote by L1 of E mu be the set of all functions on E with possibly infinite value that are integrable. Of course, with respect to mu. And I recall that this means that the integral of the absolute value is finite. So what we have is that this space, let's just call it L1, is a vector space. So we can add two functions that are integrable and stay integrable. We can multiply by real scalars. However, let's recall one issue that we had at some point, that if you might have that two functions, or that a function has as integral equal to 0, but it's not 0. But what we have is that that this implies that the function is 0 almost everywhere, which by definition of being 0 almost everywhere means that the measure, so mu almost everywhere, means the measure of all those points in E for which f of x is different than 0, then this is set as measured 0. Okay. And likewise, we have that the integral of f minus g is 0 if and only if f minus g is 0, which means f is equal to g mu almost everywhere. With this idea in mind, we should consider an equivalence class of functions. So we consider the equivalence relation. So we said that f is equivalent to g if, by definition, if f is equal to g almost everywhere, right? And therefore, f minus g has 0 integral. Okay, and we defined L1 like with a notationally different L of this measure space. We define to be L1 of E mu mod out the equivalence relation. Okay, and for a class in L1, so this we denote the equivalence, an equivalence class. The equivalence class represented by f. We set the integral, let's call it the one norm equal to the integral of f in the mu. And what we said before said that this number does not depend on the representative. So now what we have is that L1, which again is a short way, when E and mu are understood, we just write L1. L1 is a vector space this norm that we just defined is a norm, and this this norm is complete. It's complete. However, we will need to prove. So to be proved. Okay, I'm just telling you now. Moreover, this vector space is infinite dimensional. In fact, I want you to notice that if we consider the characteristic function of the interval n plus 1, this is a sequence of functions, then this is an infinite set of linearly independent functions in L1. So even after the equivalence relation, these vectors, they become linearly independent. You cannot write one of them as a finite linear combination of the others. So in other words, what we get is that L1 is an infinite dimensional Banach space. Good. I will now tell you what are some examples of Hilbert spaces, and in some sense, this will be the only Hilbert space that one has. So here's the definition: L2 of E mu. Again, we fix a metric measure space, and then we take all functions from the space E for which the integral of f square is finite, always up to the equivalence relation of before, right? F minus g almost is equal to 0 almost everywhere. We consider them the same. Okay, and for this, this is a vector space, and we define fg scalar product, the integral of f times g in the mu. And I claim that this defines a scalar product on L2 and makes L2 a Hilbert space. So here there are plenty of things to check, okay? So I'll tell you some facts that are true, but I haven't proved them yet. Okay, and we probably will not prove them today. Okay, but let's verify at least that we have a scalar product. Okay, so verification that we have a scalar product. So if you look at the function fg goes to the integral of fg the mu, right? This is what we called fg. So this function is symmetric in f and g, linear in each variable, linear. And is it positive? And it's positive. And to check that it's positive, so what we have to do? We have the integral of f squared d mu equal to 0. we have to prove that okay, this is always a positive number, non-negative number, and it is 0. If it is 0, then f squared is 0, and which gives that f is 0. Okay, so we proved that this is a scalar product. However, there is one thing we did not check. We did not really check that this number is finite. We didn't prove that this is a real number, so we need to prove that if f and g are squared integrable, then their scalar product is a finite number. Let's verify this. So we need to verify that the integral of f g d mu is finite. Okay, so now notice one thing, that if I fix a point in E, then what we have that, okay, I can take fp gp. Okay, this number, even in absolute value, this is less than f of p square plus g of p square. Okay, why is this true? Okay, let's write something. So because actually for any a and b in R, so one start with observing that a minus b squared is always greater than 0. So a squared minus 2ab plus b squared is greater than 0, which means that ab is less than actually even 1/2 of a squared plus b squared. So right, so this is what we use for numbers. Now we integrate. So we have the integral of f g d mu. This is less than the integral of f squared d mu plus the integral of g squared d mu, and it's finite if g and f are in L2. Okay, so hence the product fg is integrable. And this will be our standard example of a Hilbert space. But we still need to prove that the scalar product is complete. So let's review what we did. We considered the integrable functions, and we proved that when we consider two functions that are equivalent almost everywhere as the same object, we obtain a Banach space with this norm. Okay, here I forgot the absolute value. Okay, the absolute value of f. So this is the L1 norm. So L1 becomes a norm vector space. We did something similar. Of course, here I don't have to put the norm, it's already a square. So L2, with the same equivalence relation, now it becomes a norm vector space that actually where the norm is coming from a scalar product. Now we are going to generalize this, where here we are going to put an arbitrary exponent. The norm vector space that we will obtain, they will be called LP. So let's fix an exponent p. So p needs to be at least 1, and any element until plus infinity. Plus infinity will actually be treated but differently. Okay. Now the definition is the following. So LP of a measure space mu is by definition all those functions on the space E measurable, such that the integral of the p power of the function is finite. And always we consider the equivalence relation we consider equivalent to functions that are equivalent almost everywhere. And actually we also consider the case L infinity. L infinity is, as a set, is all measurable functions such that we don't want to say that they are bounded, but they're almost everywhere bounded. So there exists a constant such that f is less than this constant mu almost everywhere. Still, same equivalence relation. Okay, let's prove that these two spaces are naturally norm vector spaces. Actually, there will be Banach spaces as well. Okay, let's start for the case of P. So the inequality is not immediate and deserves a name. It's called Minkowski inequality. So for P in the interval 1 plus infinity, let's define the norm, the P norm of f to be the P root of the integral of f to the P. Okay, so this is the P root, or the power 1 over P of this number. Okay, so and as you see, when P is 1, okay, we obtain again the L1 norm, and when P is 2, you see this is the square root of the scalar product of f with itself, the L2 scalar product. Okay, and of course, like now this value is the same if for two functions that are equivalent almost everywhere. So now then let's consider functions f and g that are in LP. Of course, I should be more precise and write that their class is in LP, right? So let's take representative in LP. Then the norm of f plus g is less or equal to the norm of f plus the norm of g. Right? In other words, we will prove that the LP norm is a norm. Okay, let's prove. This is called Minkowski inequality. Proof. So the key point here is the fact that the function x in R goes to x to the power p R. This is convex. Okay, this would not be true if p is less than 1. So this is a convex function, and we will really make use of this. So, okay, down the page. So, if I take lambda between 0 and 1, what I have that f of x plus g of x to the power p. Let me write it this as the linear combination via lambda of two numbers. So this is lambda of f of x over lambda plus 1 minus lambda of g of x divided 1 by 1 of minus lambda. Okay, so I see this number as the linear combination of these two numbers. So I use convexity, and I obtain that this is lambda of f of x divided by lambda power p plus 1 minus lambda of gx over 1 minus lambda of p. Okay, now of course we can let me put lambda outside the norm, the p power, and what we get is, so lambda is positive, 1 minus, and so what we get, and 1 minus lambda is positive, so we get that lambda 1 minus p of f of x to the p plus 1 minus lambda 1 minus p power of g. Okay, now let's integrate. What we get is that the integral of fx minus gx where p d mu is less or equal, then I use the linearity of the integral, I forgot a p here, p in d mu. Excellent. Okay. So what we see is that the first element is the p power of the norm of f minus g. So what we wish, right? So we wish to choose lambda so that the second term becomes norm of f. So this is, yeah, norm of f plus norm of g to the p, right? This case, in this setting, we will have that this is less than this, and this is the Minkowski inequality when you take the p root. Okay, so this is what we want to do. Okay, so we have to be smart in choosing lambda. Okay, so and how it is lambda? Lambda is this parameter of linear combination between these two numbers. And now what we want to do, more or less, we want to think of averaging. You see, this is the p power of the norm of f, and this is the p power of the norm of g. Right? We have to interpolate between these two. Right? So let's call this number a. So let's define it to be a. Right? So what we have is a is lambda 1 minus p to the norm p power of f plus 1 minus lambda 1 minus p to the norm of g to the power p. Right? So what we want this to be lambda of the p norm of f plus norm of g to the p. Okay, so we try a good combination is to take the norm of f, divide by the two norms. Okay, so 1 minus lambda is norm of g divided by f plus g. So what we get? We get that a becomes so this to the power 1 minus p with power p becomes 1. So we have denominator, we have norm of f divide norm of f plus norm of g all to the power 1 minus p plus, now similarly, we have this to the power 1 minus p. This together with this makes p. Let me make it norm of g divide norm of f plus norm of g, which is again, so put this together, and this is one more times the norm of f plus g, which, so here is 1 minus p, so becomes norm of f plus norm of g to the power p. And this completes the proof of the Minkowski inequality. Okay, so now that we have the Minkowski inequality, we can write the corollary that LP together with the P norm is a norm vector space. Remember that this LP is an LP of E, and mu, right? So it might depends on the choice of mu. Okay. All right. So we proved that LP is a non-vector space. Now let's go back to the case of P equal to infinity. So case P equal infinity. Now let's define the infinite norm. So given a function, measurable function, we define the infinity norm as, so we want to say, we would say it's the supremum, but of course if the function we don't want to consider what's happening on sets of measure 0. So what we will consider is the infimum of all possible supremum. So the inf of all those c, such that the measure of the set of points on which f of x is smaller than is bigger than c, this is a set of measured 0. Right. So there might be points for which f is greater than c, but those form as measured 0 set. This can also be written as the supremum of all those point values t, such that the measure of x in E such that f of x greater than t has some measure, so it's greater than 0. So either you take, so okay, let's give a name. So this quantity, this quantity is called essential soup. Of f. So we don't consider the soup of f, but the essential soup. But you can also see it as all the essential values, the supremum of all the essential values. Okay. Now it's obvious. Let's write it as an observation that if you take two functions and you want to look at the supremum of the sum, the essential supremum, this is bounded by the essential supremum, the sum of the essential supremum. This is obvious. I mean, like, right? Because, all right, let's write something. Since so if f is almost everywhere bounded by this quantity. Okay, maybe not by this quantity because this is an infimum. So let's write plus epsilon. And G is almost everywhere bounded by norm of G plus epsilon. Then on the union of or the intersection of these full measure sets, we obtain that f plus g is almost everywhere bounded by norm of f plus norm of g plus 2 epsilon. Okay. Good. So this norm is indeed a norm, and we get as a corollary is that L infinity with the infinity norm, or the essential sup, is a norm vector space.